showing us a video of her abusing this poor cat.
All right. So I want to talk about this. This is a skeleton equation. Now, skeleton's not the Lewis dot structure, so we had to solve the Lewis dot structure. We're going to have triple bonds here and here, a double bond here, and lone pairs on the terminal nitrogens. All right. Based on that, I'm going to ask you one of the four questions. Some of y'all got at least one. Most of you got at least one of these. Some of y'all got two of these. But skeleton equations, the point is y'all need, or skeleton structures, the point is you're going to have to flesh out the Lewis dot structure completely before you can answer these questions. So go ahead and answer the following questions. This will take you a minute or two. Good? Y'all good? Yeah, again, just on your piece of paper, you're going to write 1, 2, 3, and 4. Okay, sigma and pi bonds. Remember the sigma bonds? So anything that's bonded is going to have a sigma bond, right?
Yes.
Yeah, okay, so how many sigma bonds do we have? 1, 2, 3. Let's just start. Let's do a little more organized. How about this? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 sigma bonds. Okay? Pi bonds, let's count some pi bonds. How many are here? 2, 4, 6, 8, 9. Good job. Good job. All right. You can count. So these questions are supposed to be these kinds of questions that are like breather questions. I'm taking this test. I'm doing like really hard questions. I come across the sigma and pi bond questions like, nice little reaction. Nice. Okay, back to work. Not questions you're missing. These are not supposed to be challenging questions. These are supposed to be your breather questions that instead of 90 seconds, you get to take 10 seconds or 15 seconds on them. All right. How many non-bonded electron pairs are there? 4. 1, 2, 3, 4. This question could be also asked, how many unshared electron pairs? That's another way to ask that same question. How many of these are sp2 hybridized? So sp2 means I have how many regions of electron density? I have 3 regions of electron density. How many does this one have? 2, and this one has 2, and this one has 3. So how many do I have that have 3? Just these 2 guys, right? 2. This one and this one. How many of these are sp hybridized? 8, right? I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 are sp hybridized. Like I said, there was these, there were some ring structures, and there was another couple of skeletons. It depends on what test you got because they're coming out of a bank. But again, the questions you're going to get on the test, even on the big AP exam, will be about this simple. Now, you're only going to get 1 or 2 of those, 2 at the most. But again, this is not supposed to be challenging. I mean, whether it's SP or SP2 or SP3, That's just counting regions of electron density. Okay? Good. I just want to make sure we had that down because some of the answers, and you guys need to be careful with things like this because a lot of y'all heard immediately that's not the right structure. You're right. I need you to flesh out the Lewis dot structure. Okay? All right. Good? Questions? No questions about that? Did get all your test grades put in? Depending upon where you were, you may have gotten a couple bumps up sort of the next 5. So if you were below 70, you got a little more of a boost. Everybody should be okay. Everybody still got the grades they deserve. Good? All right. Oh, why is this not working now? Yeah, that's not helpful. I wonder. All right. So, based on our discussion last class, I want y'all to solve this. And of course, you guys have homework. You got a bunch of homework that was due over the past couple days. Get that done because one of your major grades is all your daily grades. Yeah. 1, yeah. 1. Certainly 1, maybe 2. I probably do 2.
Wait, what about the...
If we don't drop any daily grades, will you add like 5 points to a major grade?
No.
Oh, you can drop 2 daily grades?
What about the...
I'm gonna drop 1. I just deleted that.
Wait. What about this?
What?
I have notes about this.
Yeah, you have your notes. Yeah.
It's not a single form.
But you're going to have, I think, at least 2 more daily assignments. There's Chapter 12. I've got 2 more sets of Chapter 12 problems. What's that? I think that's it. There may be one other thing, like a review. What's that? Yeah, if you've done 100% of the stuff, I'm going to drop 1. Maybe 2, but definitely 1. As long as you do the next ones. The Chapter 12. So what topic are we covering? Yes. We just did this. That's right. You're a little deep in the notes for this. This is early on. So there's 3 sets over here for those of you who are skipping last class. So there's one of these. Hey, don't go anywhere. You need Arrhenius made easy and this other Arrhenius.
Thank you.
Yes, we killed some trees for y'all. Hey, are you here to work or just hang out? Okay. Okay, let's make it happen, guys. Come on. You can do simple stoic if you want. It'll get you the right answer.
Wait a minute.
No.
No? Well, oh, wait. Yeah.
Do the stuff. Do the stuff.
I'm worried because like the stuff we do in here is easier than the stuff that's on the homework, and I'm not sure what we're actually testing over.
Homework, yeah. Whatever the hard stuff is.
This is the hard stuff.
No, this is the easy stuff.
It is
Okay. Y'all probably have some math you may need to work, and you're welcome to use calculators should you need them.
This isn't in the package.
No, it's not. It's what you've learned, though. Conceptually, this stuff's in the packet, yes.
No, like this, like you know how it gives example problems.
Right, I know that. Yeah. Yeah, I'm aware. All right. Is that okay? Now, the right answer, the actual right answer is not up there. I would disagree with them. They did the math wrong. But that's okay. You should figure that out, right? Is that right? Do the punchy. And most of y'all who've had sig figs beaten into you by me knows why I say that's wrong. Yes, it should be 1.4, yeah. Because here's your two sig figs.
Come on, guys, you gotta learn your squeaky figgies. Oh wait.
Remember, these are ratios. They don't count.
That's not what I was doing. They rounded the wrong way.
They rounded the wrong way, yeah. So what'd you get?
1.35.
Very good. Do y'all see how to solve these kind of problems? Super easy. Yeah. The rate of disappearance, directly proportional. Super straightforward. All right, cool. All right. Let's now talk about rate law. You're going to have to actually start thinking about math again. I know we spent a couple chapters pure conceptual, very little math, little 2 plus 2 baby math. So first of all, I want to talk a little bit about chemical reactions are reversible. This is something we've known, right? If I end up with excess energy, I can actually take energy plus those products and push the reaction back the other direction. I emphasize this in the classes that those of you who had me before, and your 5th grade teachers and your 8th grade teachers who say things like physical reactions are reversible and chemical reactions are not reversible. They're wrong. So chemical reactions are something that produces a new product. Physical reactions, we didn't change what it was. So I say, whatever you started with, if you ended up with the same thing, that's a physical process. If you started with something and ended up with something different, that's a chemical process. The example I have is if you tear paper, that's not easily reversible. But I start with a piece of paper and I tear it in half, and I started with paper and I end up with paper. On the other hand, I take a piece of paper and I burn it. I started with paper and I end up with ashes, right? So something different than I started with. I could actually reverse that process if I wanted to, if I were able to capture everything and push it back through. Now we can actually do that naturally, right? We take that ash and put it in the soil, makes a tree. Bunch of chemical processes. But we can actually do this a lot. This is a particular example. In fact, many, I would say most, chemical processes can be reversed. Now, like I said, they may require adding a lot of energy, but you can push in both directions. So, nitrogen monoxide and oxygen react, and they're going to form nitrogen dioxide. When we put these in an otherwise empty container, if I take pure NO2, it's going to degrade into nitrogen monoxide and oxygen. This is a process that can go back and forth. So we've got to be aware of that. The change in the nitrogen dioxide depends only on the forward reaction. When I start, I only have nitrogen dioxide. So initially I have no nitrogen, monoxide and oxygen. Okay? And so I'm going to be able to write this equation like this, that the rate of that is K, my constant, times the concentration of nitrogen dioxide to the power of N. Now N is the order of the reaction, and we'll be looking at that. We've got zero order reaction and first order reaction and second order reactions. So those are the reactions we're going to need to look at. By now, since we have our reading guides due, right? Hopefully y'all have already read the chapter, done the outline, gone through the whole process so that you've seen all this stuff before. You may not have understood any of it, and that's fine, but the first time you see it should not be in this classroom. And this is a good rule for college, those of y'all who might go to college, is get ahead, read the chapters before you walk into class. The class will make a whole lot more sense. Even if the chapter makes no sense whatsoever, you've started laying down those neural pathways that are going to let you pick up and go, oh, and start connecting the dots. Hopefully that'll happen. So that's my rate constant. That's the order. All right. Okay. Notice the concentration of the products are not going to appear in the rate law. The reaction rate is studied under some conditions where the reaction doesn't contribute. The reverse reaction doesn't contribute. The easiest way to do that is to start at a time zero, where there's no products to interfere trying to come back. We'll talk about that. The value of the exponent n must be determined by experiment. This is one thing I really struggled with personally when I was first exposed to this material. There's no way to look at the reaction. There's nothing in the periodic table, there's nothing in the balanced equation that can answer this question for you. It comes from data, it comes from the experiment. And so when you're doing this, just understand you've got to get the data from typically a data table they're going to give you. Okay? Don't just put that in your brain. It's got to come from the experiment. It's got to be given to you. All right. So let's look at the definition of reaction rates in terms of the consumption of nitrogen dioxide. So here's my rate. This is my rate equals this change in concentration over change in time, which is easily written as K times the concentration of nitrogen dioxide to the power of N, whatever that order is. All right, here's our definition. I can rewrite this in terms of the reaction production of O2. All right, it's going to have a O2 is this formula here. All right, let's go back here. This is another way to rate it, to write it, knowing that 2 moles of this are consumed for every mole produced. Right, because one of the oxygens is going to nitrogen monoxide, and then the other one's coming over here. So this is my 2 times the rate. The value of the constant is determined based on how the rate is defined. So that rate we could be talking about moles over time. We could be talking about molarity. Whatever it is we're talking about, that's how we're talking about ATM. However it is we're defining the rate. Now we have something that should look familiar to you math people. We have the differential rate law and the integrated rate law. This sounds a little bit like what? Yeah, so we'll have some fun here. Rate law is the other way we say this, or differential rate law. okay, is simply how the rate depends on the concentration of the reactant. So at a given time, we're going to pick a time, typically time 0, but we can pick any time we want. The rate is going to depend on the concentration, so it's not time dependent. The integrated rate law expresses how concentration depends on time. The type of rate law we use simply depends on what data is easy to collect. Sometimes it's really easy to simply measure concentration, and so that's what we measure. Some experiments lend themselves very easily. Some of the experiments we do in here. For instance, if I do an experiment that's bubbling off carbon dioxide, I can capture CO2. But if I've got a second product that just stays in the dish for me, maybe I don't care about CO2. I'm going to measure this, and then I know my balanced equation. And I can figure out how much CO2 I produce based on what I actually measured. And a lot of things are that way. If there's a product that changes color, I can measure concentration based on that. So we can use a spectrophotometer. In other words, the stuff that starts clear and stays clear I can't measure, but the stuff that's changing the color I can. So figure out what's easiest to measure, we use that. Okay. So here's an example of a table. Concentration over time data for this particular reaction. Notice at time 0 I have 1 mole, okay, and then it decreases over time. So concentration versus time. All right, differential rate law for this equation. Typically we will give you this. I can actually look at the two concentrations. I can calculate the rates. Okay? This will be often given to you. This is how you're going to see most of your data. Whatever the concentration is, whatever the rate is. And you'll remember the reason for that is we have our curves. They look like this when I plot concentration versus time. And in fact, let's go look here. So my rate at this time has this angle. This time is this one. So my slope is different, my rate is different. What this says is when my my concentration is 0.9 versus when my concentration is 0.45, if I half the concentration, I half the rate. Half the concentration is half the rate. That's what this says. So this is my differential rate law for this equation. This is a first order. My rate is this to the power of 1, and that's going to equal that. Then I can actually take that data, plug it back in, taking the experimental data, and I can actually solve for K. Because this table, I've got the concentration and I've got the rate. So I can go back here, I've got the concentration and I've got the rate, I can solve for K. And that'll be constant. So this is the rate law for the decomposition of N2O5, written out like that. Initial rates, this is right after time 0, we just call it time 0. We carry out the same experiment. We just change the concentrations. So it's all at time 0, but we just change the concentrations, and that will tell us how concentration affects rate. And we do a bunch of runs, we get a bunch of experiments, and we end up with something that looks like this. This is what's going to be given to you on a test, both mine and the AP test. This is what the kind of stuff that's going to be given to you. So I've got experiment 1, 2, 3, and 4. And at different experiments, I changed different things. So in experiment 1, my baseline experiment, I had 0.1, 0.1, and 0.1. Notice all I care about are the reactants. I've got bromate, bromide, and the hydrogen ions. Follow? Good? All right. Experiment 1, I've got 0.1, 0.1, and 0.1. That's my initial rate. So my rate at time 0, doing the math just like we did. Notice experiment 2, what was the thing we changed? Between 1 and 2, what did we change? Bromate, right. The concentration of bromate. And what did we do specifically? Doubled it. Now let's look over here. What happened here?
It's divided by 5. No, it's not. It's double.
What did I do to the concentration of this one? Doubled. What happened to the rate? Y'all get that it doubled?
Oh, okay, I see.
Exponents, yeah. Exponents are fun. All right, let's look at the difference between 2 and 3 is what? Concentration of bromide. So between 2 and 3, the concentration of bromide did what? Doubled. And what happened between the rate? Doubled. How about that? All right. 4. What should I compare 4 to? I should compare 4 to 1, right?
Because the initial concentration is double relative.
That's right. That's what you want to see. You want to make sure that only one thing, remember this is one of our things in science we do, we want to change only one thing at a time in an experiment. So in this case, I changed one thing. I did what? Between 1 and 4 is, I doubled that. What happened to this? It's what? It's 4 times. It's quadrupled. Did y'all get it? Okay. Any questions on that one? Okay. Yeah, this is a very, very simple version of what your questions might ask.
Are we going to have to understand conceptually why, like, whenever it increases the time? Because, like, for the other two, it didn't have that much of an increase.
Yeah, we'll go over the math and it'll be pretty clear.
So the hydrogen ion changes it in a second order?
Yeah, it does. Yeah, for those of you who read the chapter, yeah. That's exactly what happened. But let's do the math for those of you who didn't, which is probably the majority of you. Good here? Y'all seeing this in your notes? It's in your notes, yeah. Everybody following along? Did you find it? There you go. Yeah, see my last class, they were like, it's not in here. I said, yes it is. But anyway, they're fine.
They're special.
Yeah, they are.
Like the 4 more times.
I'm going to tell them you said that.
So I made them handwrite it.
Did you really?
So there you go. All right, so page 12, follow at home. You got your notes, page 12. There you go. Y'all good? Questions? So let's follow along from here. Let's determine the order for all the reactants, the overall reaction order, and the value for the rate constant. So the first thing I want to do is I want to draw out the generalized reaction. What's that going to be? Right, so the rate equals K. I really can't do lowercase k's, but that's a lowercase k, all right? This is bromate. Okay, and there's going to be an exponent there. I'm going to leave it blank. Let's go ahead and do N. I guess I'll write it like that. And this is bromide, because the notes do this way. And this is H plus. Good? That's our generalized equation. Now what I've asked you to do is you need to solve all of these and solve for K. Four things to do. 4 little bits of baby math. Everybody okay? All right. General form of the rate law, which is what I wrote there. I don't know what's wrong with these clickers here. The first one, I want to solve, we're going to compare these two. Because these two are the place where only bromate changes. Only bromate changes. We're only going to mess with one variable at a time, right? So let's go through the bromate. Okay. So I'm going to take rate 2, and rate 2 is 1.6 times 10 to the minus 3 over 8.0 times 10 to the minus 4. And that is K over 0.02 mole, right? Over K 0.01 mole. Now notice what's going on here. What can I cancel? I can cancel the K's. So not write those. What else can I cancel? How about these? Right? And in fact, I can actually rewrite this. This is the power of n. So 1.6 times 10 to the minus 3 divided by 8 times 10 to the minus 4 is 2. 2 equals 2 to the power of n. What would n be in order to make this truthful? N is going to be 1. So instead of n up here, I'm going to put a 1. Okay? Based on that, can you guys go ahead and solve for, the m and the p, or the exponent for the bromide and the exponent for the hydrogen ions? Yep.
What is the unit for rate? It's something per second, right?
It depends.
Yeah, what's your talent gonna be?
Has no.
Say what?
Backflip.
You can do a backflip.
No.
That's what'll make it entertaining. All right, everybody get that one? What do we get for this? Take a look at the next one here. Let's see, maybe this works. So y'all get this? Let's take a look at the next one. Let's determine the value of m. I'm going to use the results from experiments 2 and 3. Right? We just talked about that. And the nice thing is the concentration of bromide did what? Doubled, and the rate did also what? Doubled. So that's going to be what order?
First order.
That's going to be another first order. Let's see what that does. So m is going to be 1, another first order. Let's go ahead and write that down. All right. Let's take a look at P. P, on the other hand. And I love these way these click up into place. So P quadrupled. If I doubled it, it quadrupled. Therefore, my P is going to be what? 2. So that's going to be a second order. I'm going to change this to a 2. A second order reaction. So the overall reaction order is you add these two together, all these together. I'm going to tell you, you're probably not going to have overall reaction orders of 4 on your exam. It makes life a little more complicated. Okay, so it'll be pretty simple ones, right? But you need to be able to recognize things like if I double the reactants, and it quadruples the rate. Yeah.
So would we have to show the working credit for that, or if we can just look at it and recognize that?
So for multiple choice, no.
Okay, so for
For response, you would. Or you could just, this is a great question though. So another question, I don't have to do all this math. I could literally write the statement. The reaction rate quadrupled when it doubled, therefore. Simple stuff. You don't have to show all this math. You can just, but you got to tell them how you got there. You can't just write 2. You could start with that. All right. Given that, now we can solve for K. So now we have the reaction. Now we have rate, and we have all of these from any one of the experiments. From any one of the experiments. And here's actually a good way if you're checking it, because if you would like to publish a paper or something, you would do this equation with all of the experiments. And your K should be really close to each other, regardless of which one you chose, right? Because otherwise, something's wrong. So let's go ahead and try that. We can do this. There's the rate law. I can actually grab the initial experiment. I like the initial experiment because it's all a bunch of ones. Okay, so I can actually plug this in. The rate is 8.0 times 10 to the minus fourth. I've got some units for that. Equals K times 0.1 to the power of 1, which I'm just not even going to write. 0.1 squared. I guess, right? Is it 0.1? Yeah. Okay, there's a bunch of units on here. The units look really funny. Just keep up with your units, because they may look a little different every time you solve it. All right, so there we go. So could you solve for K now?
Yes.
Yeah, y'all know how to solve for K, right? There. Y'all watch those units. See how funny those units look? Everybody okay? Yep. Questions on this? Okay. All right. Well, let's see if you know what you're doing. Your turn. You can't just guess. Do your work. Justify your answer. This is not in your packet. This is one of the brand new join-ins. So y'all gonna need to find some scratch paper. Yeah, don't spend 20 minutes looking for it. Come on. There we go. All right. So this is my general rate law, right? Rate equals K, concentration of A to the power of N, concentration of B to the power of P. Solving for N looks like this, right? Everybody follow that. So N in this case is going to be 1, right? So 2 equals 2 to the power of N. N equals 1. All right, so I'm going to go up here. I can change this to a 1. Did everybody get that one? You got that one, right? Let's look at the next one. I'm going to compare these two, right? These two, because this is the same and this is different. So let's compare that. So 0.3, Stu, 0.060 divided by 0.060 equals 0.30 divided by 0.20, the power of P. Everybody okay with that? All right. 0.060 divided by 0.060 is 1. And 1 is 1.5 to the power of P. What is the only thing P can be? 0. In this case, P is 0. This is 0, and since it's 0, anything to the power of 0 is? No, anything to the power of 0 is 1. Very good. So my answer should be, hey, the rate of this reaction is solely dependent upon the concentration of A.
Oh, crap, that's right.
Everybody good with that now?
I'm so confused because I was looking at it like it was the original and then the initials on this side.
Yeah, this is again, yeah, reading tables The other tables turn sideways. Yeah, we just got to watch that. And you'll probably get tables that look like this or like the little 4, little simple little things. Y'all good with that? All right. Let's see. Oh, I need to go back and.
For like questions on the AP test, would they give us still at like A and B, or would they do like actual?
No, they could give you actual chemical reactions, or they could give you just A's and B's. Either one's quite possible. Let's see. All right. We're now going to talk about the integrated rate law. So the integrated rate law is used to express reactant concentrations as a function of time. And that's how we draw our rate. First order reactions. First order reactions is a rate law for the decomposition of nitrogen pentoxide. This is a first order reaction. First order means that the N, or whatever that exponent is, going to be 1. The rate of formation of products increases with the increase in the concentration of the reactants. I mean, this is what this means. You're going to need to know about first order reactions. So 0 order, first order, second order. If you know those, you'll be in good shape. There's other things that are going on, but really on the AP test, they're not going to push you on that stuff. First order reactions you can convert to an integrated rate law using natural logs. And we do this because it makes nice little pretty straight lines. And if we make nice little pretty straight lines, once we do that, then we can solve, right? And I point that out because if you'll remember our little graph, and if I'm just using concentration and time, typically we're going to see curves that look like this, right? We've shown you a couple of those. And in fact, if I have a point here that I took a measurement on and a point here that I took a measurement on, can you tell me what the rate is at this point? Based on this graph, based on the way I drew it? No, I mean, I could probably get you in the ballpark, but no, I can't, because you do that by doing straight lines, and then I didn't do a straight line. There we go. So you can see that's close. But that's not going to be exactly right. The point is not going to be halfway between there. It's not how this works. So, but if I can convert that to a natural log, I can make a straight line, and then I can answer those kinds of questions. All right. So I don't want to do this. We'll take a look at our reactions and see what happens. So instead, I rewrite this as the natural log of the concentration equals negative kT plus the natural log of concentration at time 0. This is for first order reactions. This only works on first order reactions, because second order curves are going to look different, right? All right. So here's our integrated rate law. The integrated first order rate law looks like this. This should be on your formula sheet, right? On the top of your page, you're going to see 3 different graphs. I can almost bet you a pack of Smarties that you're going to have a question that just has pictures of graphs and ask you which one is a first order, which one's second order, which one's 0 order. Y'all have that? I think it's at the top of. Yeah. Yep. Oh yeah, there it is, yeah. Okay. Know those graphs. Know those 3. You're probably going to have a question on the test that asks you what order is this just based on the graph of the data. All right? So here we go. The equation represents the influence of time on the concentration of A. So first order graphs look like this. Same thing. I don't know why they wrote it out with long words like that, but that's what that is. This allows us to get a nice y equals mx plus b line. For first order reactions, a plot of the natural log of the concentration versus T is a straight line. So m is negative k, because k's got to be positive, but that's going to be negative k, negative slope, and your b-intercept is your natural log at time 0, which is something up here, right? Because you're always going to start with something above 0, and you're never going to go below 0. All right. Good? All right. Rewrite that as this. So, y'all see that? Natural log of the initial concentration over the concentration at time t. I could write a little t there. Equals k times time.
For the cheat, well, not cheat sheet, but
The formula chart?
yeah.
Yeah. Yeah, these are on your, the formulas you need, the equations you need are on your equation chart.
Yeah, the equation.
Yeah. All right. Go ahead and do this. Notice I don't have a measurement at 150 seconds. But using this formula, I should be able to solve for 150 seconds. Now, logically, when I get done, it's going to be between these two, right? I know it's going to be less than 0.05 and greater than 0.025. But it's not going to be exactly in the middle. That's my thinking there. So we need to solve for that. Using the equations, go ahead and solve for the concentration of N2O5 at 150 seconds after the start of this reaction. Can y'all do that?
It's on page 14.
It is. Okay, this is your K. K is 6.93 times 10 to the minus 3. So if I give you this, can you determine K? You can determine the rate for each of those. And you can use the rate for each of those to solve for K. I just want to make sure y'all can do it. We're not going to do it. I gave you K, so I wanted you to just have it. But you can, given this data, solve for K yourself. We may do that next class when we get through the integrated rate law. There's K. So given K, should make this problem a whole lot easier to solve. Everybody got it? Still working? Remember our formulas. We'll click through this real quick. There's our formula. So at this point, hopefully you can just plug these numbers in, right? Okay. I see some consternation in the back of the room. Is there questions? What's that?
I think you just need to see like it, because the answer that I got isn't at the bottom of this paper.
Why aren't we doing this stuff?
Because I'm lost. I'll take it to you.
Write that equation. Fill in the blanks. So, t is 150 seconds. K is this number. The time at 0 is 0.1, which goes here. So when I get all done, it's natural log and I'm not going to worry about units. Okay. Did y'all get that? What's that? Oh, I got the T. Yeah, that's what I knew. I forgot something. There we go. Let's get that fixed. That's a plus, right? Oh, the paper has for a different time? Well, okay. That makes sense then. All right, here we go. That's what I just wrote there, I think. So, all these things cancel out. Take the anti-log. Hopefully everybody got that right. You know how to use your calculator, the little shift to ln or e to the power of. What's that? Okay. The logarithm and anti-log. Yeah. But how do you get the anti-log of a number? Yeah. Yeah, that's so you do second, and that's whatever that is. No, that's the other log. You need this one. Sorry. So it's this, and then answer. Whatever you do to get answer. Oops. Whatever you do to get answer. So you could do that, right? So you could do
The letter.
minus 3.43.
342.
There you go. Yep, sorry, man. Good? Does everybody know how to get this now? Good, excellent test questions. Or pop exam next class, right? Yep. Okay. Yeah. Questions on this? All right. I'm going to call it a day. I know we're way early, so y'all feel free to get your work done. What's that? Sure.